This is going to be a short lecture on tools for topological data analysis. The idea is to give you links to various resources that you can follow in order to experiment and apply these tools for the data sets that you are going to encounter later. So thanks to Raghavendra for the slides that I'm going to present on Scikit TDA, and thanks to Mohit for giving me the slides on TTK. There are several software resources available for TDA. The idea here is not to list all of them, but to talk about a few that are unique and also heavily used, popular. I'm going to mention only one commercial tool, which is ISD. We have talked about this in class. ISD is a ML company which began by looking at a TDA and is one of the pioneers in this area. The founders are the creators of the mapper algorithm. For those of you who have used the statistics package, there is a very nice TDA package within R that incorporates implementation of persistent homology and distances between persistence diagrams from multiple sources and allows the user to choose specific implementations. Goody is a project from India that focuses on efficient computation and has implementation of persistent homology, regular homology, various simplicial complex and their filtrations. Locally within IISc, we have developed software for computing various topological structures, including the Morse-Mail complex, the contour tree, merge tree, topological structures for two fields, including the Jacobi set, and tools for simplifying and creating hierarchical representations of these topological structures. So I'm not going to talk about any of these packages in detail. So similar to the above, there are several software packages available with specific functionalities. What I have mentioned earlier were the more generic toolkits that support multiple functions. So the software such as Javaplex, Perseus, and so on have more kind of limited functionality, but nevertheless efficient and useful implementations. This link lists is an up-to-date list of various software tools that are available for TDA. I am going to talk about Scikit TDA and TTK. Let's start with Scikit TDA. Scikit, as you all know, is a Python-based library that supports functions related to machine learning, vision, image processing, and so on. The unique feature of Scikit is that it is all written in Python and easy to set up and run. Scikit TDA is a specific tool for topological data analysis, and a unique feature of Scikit TDA is that it is a collection of tools that have a common interface. For example, Ripser, Mapper, Persim, and so on have been developed outside of Scikit, but can all be called from within Scikit. This makes it quite powerful. Scikit TDA is easy to install and use. It just requires Python 3, and it's based on an Anaconda installer and Jupyter notebooks. Scikit TDA can be used for computing various quantities, including persistence homology. It can be used to compute persistence diagrams and display them. It can be used to compute other representations of persistence diagrams, such as persistent images, and compute distance between these persistence diagrams and other quantities on persistence diagrams. Finally, it can be used to compute filtrations using simply shell complexes, such as the check complex, RIPS complex, the alpha complex. Processing data and analyzing data using Scikit TDA is quite easy. So there is a small snippet of a code here. So computing the RIPS complex is as easy as just calling the RIPS functionality, followed by the computation of the persistence diagram, and displaying the diagram is as easy as just calling a plot function. So this code will generate output such as this, where you have the point cloud shown on the left, essentially a scatter plot, and you can see that the point cloud is noisy, but it has some circles, and the persistence diagram is shown on the right. The persistence diagram includes the H0 homology and H1, shown in two different colors. So the Scikit TDA includes the functionality for displaying the result as well. There is good documentation, and documentation for the individual tools, of course, is available from within their web pages. To summarize, one of the salient features of Scikit TDA is the ease of use and the fact that it is embedded within a popular and a popular environment that is used for other data analysis tasks. TTK is a tool or a software platform for topological analysis, primarily for scalar data, and was developed within the visualization community. It's relatively a more recently developed tool and is under active development. It contains a collection of various algorithms for computing topological structures. It is developed on top of a visualization toolkit called VTK, and it uses the visualization software ParaView for all the UI. More recently, there are integration into other visualization software such as InVivo. It supports scalar fields and point clouds. More specifically, it can be used to compute topological structures for univariate, as in single scalar fields, but it also supports topological structures that are defined and computed for bivariate data, for data that comes with uncertainty, for time varying or dynamically changing data, and for point cloud data or high dimensional data. Similar to other TDA tools, TDK also supports the computation and display of persistence diagrams. Unlike the other tools, TTK is really good at the visualization of the output, and the fact that it's integrated within ParaView means that interaction with this output is also sophisticated. TTK supports a simple implementation of the Morse-Mel complex, and fast parallel algorithms for computing the contour tree and the merge tree, and for displaying individual isosurfaces and isocontours. Like I mentioned, one of the specialities of TTK is the high quality visualizations of the topological structures and for example, the scalar field. It also supports the processing of multiple bivariate fields, which is a collection of two scalar fields, and here it allows for the computation of the generalization of the isosurface to something called the fiber surface, and the generalization of the critical points to something called the Jacobi set. In addition, TTK allows the users to write scripts and create their own modules. Here are some visualizations using TTK. On the left, you see a CT scan of the foot, which is visualized by the application of color and transparency. And what you see on the within that figure is also the persistence diagram, which clearly shows that there are certain components having high persistence. So the figure on the left is created by using the persistence diagram to identify the critical points to preserve, and those critical points that need to be simplified. The figure on the right is a visualization of atoms in molecules, where the input is the electron density distribution over the molecule together with its gradient, and this is used to generate the so-called fiber surfaces that help visualize the individual atoms within the molecule and the bonds. Salient features of TTK include fast, efficient computation. Often the algorithms are parallel and work on the GPU, often on multi-core CPU. Another important feature of TDK is that the underlying data structures that support all the computation is efficiently designed. For example, it supports caching, where the motivation is that all computation or several algorithms require the traversal of the domain, and the cached data structure for the simplicial complex or the triangulation within TTK, it supports very efficient query. For example, given a vertex, it allows the algorithm to access all the edges, triangles, and tetrahedra, the 1, 2, and 3 cofaces efficiently. Similarly, it allows for efficient access for the cofaces of an edge, the cofaces of a triangle, and so on. Now, the way TTK supports these efficient queries is by allowing the user to prep up or precondition the data structure so that these queries can be answered efficiently. The facility to precondition essentially means that the data structure can be set up as and when required. This is a very nice feature. The TTK is available open source, and the documentation is also available at this link. So with that, I end this discussion on TDA tools. There are, of course, several details that are available within the documentation, and this is something that you learn by getting your hands dirty. So with that, we come to an end of the discussion on TDA tools. Good luck analyzing your data using these tools.